At Kīlauea's summit, the landscape is changing again, and this time the change is not simply another burst from the familiar fountains. A new opening has entered the volcanic system. The United States Geological Survey has confirmed that a collapse pit on the slope behind the south vent formed a new west vent during episode 53 of the ongoing Halemaʻumaʻu eruption. That confirmation matters because Kīlauea has spent nearly 2 years repeatedly erupting through a remarkably consistent pair of openings, the north and south vents. Now the architecture of the eruption has changed. As of August 18th, the volcano is paused, but the pressure beneath it is rebuilding, and USGS expects another fountaining episode most likely between August 21st and August 27th. The timing is extraordinary. Episode 53 began at approximately 3:45 in the afternoon Hawaiian Standard Time on August 12th and ended abruptly at 1:23 in the morning on August 13th. For roughly 9.6 hours, molten rock surged from the summit system, with the north vent producing the dominant fountain. At its maximum, that fountain reached approximately 500 feet, or 150 meters, above the surrounding ground. A volcanic plume climbed to roughly 18,000 feet, or about 5,500 meters above sea level. But while the north vent commanded the spectacle, something else was happening nearby. The collapse pit behind the south vent had become an active opening of its own. That opening is now being referred to by USGS as the new west vent. It did not behave like a completely independent fountain during episode 53. Instead, it produced precursory overflows and periodically emitted flames, especially after about 7 in the evening. That distinction is important. A vent can exist without immediately producing a towering lava fountain. Magma, gas, heat, and pressure can move through an opening in different ways depending on the pressure inside the shallow plumbing system. At Kīlauea, the new west vent therefore represents something more significant than a glowing hole in the crater. It is evidence that the pathways through which magma reaches the surface are capable of changing even after months of apparently repetitive behavior. The image captured on August 12th gives a remarkable visual clue. The familiar north and south regions of Halemaʻumaʻu are no longer the entire picture. A section of the volcanic terrain behind the south vent has collapsed, exposing a new depression and opening a pathway that can interact with the magma system. The fire visible through the darkness is not simply surface rock glowing from the nearby eruption. The intermittent flames observed by USGS indicate that hot volcanic gases and incandescent material were reaching the surface through this newly formed opening. In volcanic terms, that is a warning that the summit is still mechanically active, still adjusting, and still capable of rearranging the places where pressure finds an escape route. The new west vent also reveals something fundamental about Kīlauea. An eruption does not need to migrate miles across the volcano to become more complicated. Changes can happen within a relatively small area because the shallow summit plumbing system is fractured, pressurized, and constantly responding to the removal and addition of magma. The current eruption has remained concentrated inside Halemaʻumaʻu and the summit caldera, rather than opening a new eruption far down the East Rift Zone or Southwest Rift Zone. USGS reports that seismicity and ground deformation remain low along those rift zones. The important movement right now is happening much closer to the summit, where magma pressure rises and falls beneath the eruptive vents. To understand why the new west vent matters, it helps to return to the beginning. The present summit eruption started during the early morning of December 23, 2024. USGS reported that fissures on the caldera floor began erupting lava fountains and feeding lava flows inside Halemaʻumaʻu and onto the downdropped block within Kūlauea, Kīlauea's summit caldera. The eruption immediately established the basic ingredients that would define the following months: shallow magma, fissures, lava fountains, pressure changes, and repeated transitions between eruption and pause. What eventually became the familiar north and south vents emerged as the activity concentrated into particular openings within the western part of Halemaʻumaʻu. Those two vents became the central engines of the eruption. USGS describes the north and south vents as the primary eruptive openings in Halemaʻumaʻu, with lava fountains and lava flows repeatedly emerging from them. Their behavior was never perfectly identical. Sometimes both were active. Sometimes one dominated. Sometimes one produced overflows while the other generated a fountain. Their shapes also changed as lava accumulated around them, building cones and modifying the local terrain. This is one of the most fascinating characteristics of the eruption. The vents are not fixed pipes carved permanently into the volcano. They are evolving structures whose geometry changes as lava erupts, cools, collapses, and is buried beneath newer material. The North Vent eventually became the dominant fountain source during much of 2026. By the time episode 53 arrived, that pattern was unmistakable. Episodes 44 through 48 were dominated by North Vent fountaining, while the South Vent continued to contribute precursory lava flows or overflows. Episodes 49 through 52 continued the pattern, with the North Vent producing the principal fountains. Episode 53 again sent the main fountain skyward from the North Vent, reaching approximately 500 feet or 150 meters. The South Vent overflowed before the main fountaining began, but never developed the principal fountain during that episode. That long-term behavior is important because it shows why the new West Vent should not automatically be interpreted as a replacement for the North Vent. Volcanoes rarely obey simple schedules. A new opening can become dominant, remain secondary, close, reopen, or simply provide another pathway for gas and lava. At Kīlauea, the balance between pressure, rock strength, vent elevation, and the geometry of shallow cracks determines where magma can move. The North Vent has repeatedly demonstrated that it can handle large eruptive flows. The new West Vent has so far shown a much more limited behavior. It produced overflows and flames during episode 53, but USGS has not reported it producing a major sustained fountain comparable to the North Vent. The geology behind the new opening becomes even more interesting when compared with an earlier change in the eruption. In August 2025, episode 30 produced a new fissure in the southern part of Halemaʻumaʻu. USGS scientists found evidence that a shallow dike had been injected into the surrounding rock. Earthquakes and deformation showed magma moving through a newly opened pathway before reaching the surface. The fissure demonstrated that the eruption could alter its plumbing system when pressure became high enough and when magma encountered weaknesses in the surrounding rock. That event was a major reminder that even a repetitive eruption can suddenly change its geometry. The new West Vent is another expression of that same fundamental volcanic principle. There is, however, a crucial difference. The new West Vent associated with episode 53 was formed when a collapse pit developed in the slope behind the South Vent. In other words, the surface terrain itself failed and created an opening that became connected with the eruptive system. USGS now explicitly describes that collapse pit as having formed the new West Vent. That is different from simply saying that magma broke through an untouched section of ground. The collapse altered the physical structure around the existing South Vent area, creating another place where heat, gas, and eruptive material could emerge. It is a reminder that volcanic plumbing and volcanic landscape are constantly influencing each other. Imagine the summit system as a pressurized network rather than a single underground tube. Magma is stored and transported through interconnected reservoirs, cracks, conduits, and fractures. When pressure rises, magma pushes against surrounding rock. If the rock can withstand that pressure, the system continues to inflate. If weaknesses open, magma and gas can exploit them. When an eruption begins, pressure drops as material leaves the system and the summit deflates. After the fountains stop, magma begins accumulating and pressurizing the shallow system again. USGS monitoring of Kīlauea has repeatedly recorded this inflation and deflation cycle. The new West Vent emerged during that constantly changing mechanical environment. The most remarkable feature of this eruption is therefore not simply the height of its fountains. It is the repeated pressure cycle underneath them. During an eruptive episode, the shallow magma reservoir loses pressure as lava escapes. Tilt meters record the associated deflation. Then the eruption stops, and the system begins to recharge. Ground deformation reverses as magma accumulates and pressure builds again. That produces the characteristic sawtooth pattern that scientists have been tracking. Each eruptive episode becomes one more cycle in an enormous natural pressure experiment. The volcano effectively fills, releases, deflates, pauses, and begins filling again. The new west vent appeared during one of those cycles, showing that the physical pathways can evolve while the larger pressure rhythm continues. By August 17th, USGS reported that Kīlauea was not erupting and that the summit eruption remained paused. The volcano was at alert level advisory, with an aviation color code of yellow. The latest official update available, as of August 18th, stated that the next fountaining episode was preliminarily expected between August 21st and August 27th. That is not a precise appointment on a calendar. It is a forecast window based primarily on the observed pattern of summit reinflation. Volcanic systems can accelerate, slow down, or experience temporary deflationary excursions that alter the timing. USGS specifically warns that these deflationary steps cannot be forecast reliably and can interfere with normal episode predictions. The pressure signal is already significant. Following episode 53, the Wekahuna tilt meter recorded a total of approximately 7.4 microradians of inflationary tilt by August 17th. There was a complication. Rapid inflation immediately after the eruption shifted into mild deflation on August 14th. Another inflationary phase then resumed, increasing by approximately 2.6 microradians during the following 24 hours. That stepwise behavior resembles the pattern that preceded earlier episodes. The volcano is not simply inflating smoothly like a balloon. Instead, the summit appears to recharge in pulses, with brief interruptions and reversals before pressure builds again. For scientists, those subtle movements are critical clues about when the next eruption may begin. That makes the next episode especially interesting because the new west vent is now part of the physical landscape. USGS has not said that the new vent will definitely erupt during episode 54, and there is no scientific basis for claiming that it will suddenly become the dominant fountain. Several outcomes remain possible. The north vent may continue producing the principal fountains, while the west vent contributes flames or overflows. The west vent may become more active. The south vent may regain a stronger role. Multiple openings could operate together, or the new opening could remain comparatively quiet. The key point is that the eruption now has another known pathway capable of interacting with the shallow magma system. The north vent itself demonstrates why predicting the winner is difficult. Across the many episodes, activity has shifted between the north and south vents. During some periods, the south vent produced impressive fountains. During others, the north vent dominated almost completely. Episode 38 in December 2025, for example, featured a powerful inclined fountain from the south vent that reached roughly 300 meters or about 1,000 feet. Later episodes shifted strongly toward the north. The system therefore has a history of redistributing eruptive power. The new west vent adds another variable to that already complicated balance. The chemistry of the eruption adds another layer. During pauses, summit sulfur dioxide emissions typically remain in the range of roughly 1,000 to 5,000 tons per day. That does not mean Kīlauea is erupting continuously at the surface. It means the volcanic system continues releasing gases even while the fountains are paused. Sulfur dioxide is particularly important because it can react in the atmosphere and contribute to VOG, or volcanic air pollution. Gas behavior can change as magma rises, degasses, and moves through different pathways. A new vent may therefore matter even when it is producing only intermittent flames rather than a spectacular fountain. The absence of a giant lava jet does not mean the opening is geologically insignificant. The next episode may also reveal whether the new west vent is becoming structurally established. A vent that survives one eruption may be gradually enlarged by repeated erosion, collapse, lava deposition, and thermal fracturing. Every burst of magma can modify its walls. Every pause allows some of those walls to cool, crack, and slump. Over many cycles, an opening can become larger and more stable, or it can become blocked by solidified lava. The volcano is effectively rebuilding its own plumbing architecture in real time. USGS has repeatedly documented changing vent geometries throughout this eruption, including growing cones and shifting eruptive areas. The new west vent is entering that evolutionary process at a particularly fascinating moment. The lava itself has already transformed Halemaʻumaʻu on an enormous scale. By the end of episode 53, USGS estimated that approximately 6 million cubic yards, or about 4.6 million cubic meters, of lava had erupted during that episode alone. Lava covered roughly 40 to 50% of the crater floor. That material does not simply disappear when the fountains stop. It remains hot, slowly cools, fractures, and can continue moving under gravity. Some surfaces may remain incandescent for days or longer. Each episode therefore leaves behind a new layer of volcanic architecture, gradually raising and reshaping the crater floor while changing the slopes around the vents. The cumulative effect is extraordinary. After the first year of this eruption, USGS reported that the Halemaʻumaʻu crater floor had risen by more than 220 feet, or about 68 meters in places. A new volcanic cone, approximately 140 feet, or 42 meters, high, had also developed along the western portion of the summit landscape. The eruption has been constructing terrain almost as quickly as it destroys or reshapes it. The new west vent is appearing within that constantly rebuilt environment. It is not being born on a pristine volcanic surface. It is emerging in a landscape already buried beneath repeated layers of lava, spatter, tephra, and collapsed material. There is another reason the new opening deserves attention. It shows that collapse itself can become part of the eruptive process. At Kīlauea, the walls and slopes surrounding Halemaʻumaʻu are not rigid concrete structures. They contain fractured volcanic rock, layers of lava, tephra, older deposits, and zones weakened by previous deformation. When magma pressure changes, when lava accumulates, or when gravity acts on steep, unstable slopes, sections can crack and slump. A collapse can expose hotter material, change the shape of a vent, or create a pathway through which volcanic gases and magma can interact with the surface. The new west vent demonstrates that the surface can become an active participant in reshaping the eruption. Scientists will be watching several signals as episode 54 approaches. Tilt meters will show whether inflation continues. Seismometers will detect changes in tremor and earthquake activity. Gas instruments will track sulfur dioxide emissions. Webcams and other visual systems will search for renewed glow, flames, spattering, overflows, and changes at the vents. Satellite observations can reveal deformation and new lava deposits over areas too dangerous for routine field access. None of these instruments alone provides a perfect forecast. Together, however, they create a detailed picture of the volcano's changing pressure state. That network is what makes it possible to recognize subtle changes before they become obvious to the human eye. There is also a warning hidden inside the apparent predictability of Kīlauea. The eruption has developed a recognizable rhythm, but recognizable does not mean guaranteed. USGS has emphasized that deflationary excursions can interrupt the inflation pattern and make the timing of future episodes difficult to forecast. Earlier changes have also demonstrated that new fissures and openings can appear. Episode 30 in 2025 produced a new southern fissure after shallow magma moved into a crack, while episode 53 produced the new west vent through collapse-related changes behind the south vent. Kīlauea can therefore preserve a pattern for months and then alter its plumbing within a single episode. For anyone watching from outside Hawaii Volcanoes National Park, the most important fact is that the active eruption remains within a closed area of the park. The current USGS status is advisory, not a declaration that a major dangerous eruption is imminent outside the summit. There is also no significant activity currently reported along the East Rift Zone or Southwest Rift Zone. But the summit itself remains hazardous. Volcanic gases can remain dangerous downwind, tephra can irritate the eyes and respiratory system, hot lava can continue moving after fountains stop, and unstable crater walls can produce rockfalls and collapses. The closed areas around Halemaʻumaʻu remain closed for a reason. The aviation picture is also worth remembering. During episode 53, the volcanic plume reached approximately 18,000 feet, or about 5,500 meters, above sea level. That is high enough for volcanic emissions to become an aviation concern, depending on wind conditions and particle concentrations. The aviation color code has since returned to yellow because the eruption is paused, but the next fountaining episode can rapidly change the situation. Lava fountains inject gases and fragmented lava into the atmosphere, while winds determine where lighter particles and volcanic gases travel. The location and height of future fountains will therefore matter just as much as their brightness when assessing potential impacts beyond the crater. Perhaps the most intriguing possibility is that the new west vent marks the beginning of another chapter in Kīlauea's evolving summit architecture. That does not mean a dramatic migration is underway. There is currently no evidence that the eruption is moving away from the summit system or toward populated areas. Instead, the evidence points to something more subtle and scientifically fascinating. The existing eruption is modifying its own pathways. The north and south vents established the dominant pattern. Episode 30 demonstrated that new fissures can develop. Episode 53 has now added a confirmed west vent formed from a collapse pit behind the south vent. The volcano is effectively rewriting the map while the eruption continues.